What specific problem does the mixtures of in-context learners MOICL method aim to solve in the context of in-context learning ICL with large language models?
The mixtures of in-context learners MOICL method aims to address several limitations inherent in traditional in-context learning ICL with large language models LLMs. Specifically, it seeks to improve the selection and weighting of demonstrations, which are often chosen heuristically and can lead to suboptimal performance due to noise or irrelevant examples. MOICL dynamically learns the contribution of different subsets of demonstrations by assigning weights to them, allowing the model to identify both helpful and harmful examples, anti-experts. This method enhances generalization by effectively mitigating the impact of out-of-distribution demonstrations and label imbalance, which are common challenges in ICL. Additionally, MOICL reduces computational complexity associated with self-attention operations by partitioning demonstrations into subsets, thus improving data and time efficiency.
How does the proposed MOICL method work? Please illustrate the process step by step, including how subsets of demonstrations are formed and how the mixing weights are determined.
The proposed mixture of in-context learners MOICL method works by first partitioning a set of demonstrations, D, into K disjoint subsets, D_1 L D_K. Each subset is treated as an expert and is passed to the large language model, LLM, along with the input text, X, to generate next token distributions. The next step involves determining the mixing weights, W_I, for each expert, which can be done using either scalar weights initialized uniformly or through a hypernetwork that generates weights based on the concatenated subsets. These weights are then optimized via gradient-based methods to maximize the conditional log likelihood of a training set. Finally, the next token distributions from all experts are combined using the learned weights to produce a final output, allowing MOICL to dynamically identify and leverage the most relevant demonstrations while mitigating the influence of noisy or out-of-distribution examples.
Can you provide a simple yet illustrative example that demonstrates how MOICL processes input data and combines the outputs from the different expert subsets?
MOICL processes input data by first partitioning a set of demonstrations, D, into K disjoint subsets denoted as D_1 D_2 L D_K. Each subset is treated as an expert, and the model generates next token distributions for each expert based on the input text, X. These distributions are then combined using a vector of mixing weights, W, where each weight, W_I, represents the contribution of the ith expert to the final output. For instance, if D_1 contains high-quality demonstrations relevant to the task, it may receive a higher weight compared to D_2, which might contain noisy or irrelevant examples. This dynamic weighting allows MOICL to effectively leverage the strengths of different subsets while mitigating the influence of less useful or harmful demonstrations, ultimately producing a more accurate prediction.
What are the theoretical or practical benefits of using MOICL compared to traditional concat-based ICL methods?
The mixtures of in-context learners MOICL method offers several theoretical and practical benefits over traditional concat-based ICL methods. Firstly, MOICL dynamically assigns weights to subsets of demonstrations, allowing it to identify and leverage both helpful and unhelpful examples, which enhances generalization and performance, particularly in the presence of out-of-distribution demonstrations and label imbalances. Secondly, it significantly reduces computational complexity by partitioning demonstrations into subsets, thus mitigating the quadratic growth of self-attention operations associated with increasing context length in transformer-based models. Additionally, MOICL demonstrates resilience to noisy demonstrations, maintaining performance levels even as the number of noisy inputs increases, unlike concat-based ICL, which suffers a performance drop under similar conditions. Finally, MOICL is more data efficient, achieving better results with fewer annotated demonstrations compared to concat-based ICL, which struggles when the number of demonstrations exceeds the context length limit.
How does the validation process for MOICL work? Discuss the datasets used, evaluation metrics, and any comparisons made with baseline methods.
The validation process for mixtures of in-context learners, MOICL, involved extensive experimentation across various datasets, including tweet-eval offensive hate, SST2, RTE, fever, pause, and QNLI for classification tasks, and natural questions for open-ended generation tasks. The evaluation metrics used were accuracy for classification tasks and exact match M for generation tasks. MOICL was compared against several baseline methods, including concat-based ICL, random search, ensemble-based ICL, and a parameter-efficient fine-tuning method called LoRa. Results indicated that MOICL outperformed the baseline ICL methods on most datasets, particularly achieving significant accuracy improvements in tasks like hate and offensive, while also demonstrating resilience to noisy demonstrations and label imbalance. The experiments highlighted that MOICL's performance was not significantly affected by the choice of partitioning methods, reinforcing its robustness in various settings.
What specific results were achieved with MOICL across different datasets, and how do these results compare to the performance of the baseline methods?
MOICL demonstrated superior performance across various datasets, notably achieving significant accuracy improvements compared to baseline methods. For instance, in the hate dataset, MOICL achieved an accuracy of 66.52 with K equals 10, which is approximately a 10-point increase over the concat-based ICL. In the offensive dataset, MOICL reached an accuracy of 81.33 with K equals 30. However, it performed similarly to concat-based ICL on the SST2 dataset and showed lower performance on the RTE dataset. Overall, MOICL outperformed baseline methods like concat-based ICL in most cases, particularly excelling in handling noisy demonstrations and label imbalance, thereby showcasing its robustness and efficiency in various classification tasks.